think that there's an effect that you test it for, when there actually is no effect, right? And false negatives are just when you conclude that there's no effect, right? When there actually is one. And since you have these two kinds of mistakes, right, since there's this kind of inductive risk problem, scientists need to make a decision on what counts as enough evidence for accepting a particular claim. And the goal here in this talk that I have is kind of really modest. I would like to explore how scientists set to decide what counts as enough evidence for accepting a claim that a given behavioral, cognitive, or neural feature correlates with, facilitates, or depends on consciousness. And I want to make 3 points. So the first one is that scientists suggest that many scientific studies of consciousness these days, they rely on evidential standards of statistical significance that are based on the value judgment that false positive errors are much more problematic than false negatives. And I want to suggest that this kind of value judgment underlying in studies can actually hinder maybe the discovery of correlates of consciousness or science of consciousness, the best process. And then I want to suggest that actually recent efforts in sort of the meta-science debate, where people are trying to improve science by rigidifying or making the kind of benchmarks for statistical significance more conservative, these kinds of efforts, they can actually further increase the risk in the domain of consciousness research, the risk of overlooking consciousness effects. Okay, so, but maybe let's just start with a common intuition, right? So let's take a step back. And so if you're probably more familiar than me with the literature on animal consciousness, and sort of consciousness in brain organoids. But so if you look at this literature, you will find that it's a very common view that false negatives in consciousness descriptions are particularly problematic. So the idea is that when organic or an artificial system is mistakenly viewed as not conscious, even though it is conscious, then that may actually have harmful effects for that system rather than benefit it, right? And in contrast, when the system is mistakenly viewed as conscious, even though it is not conscious, that wouldn't really cause much harm to the system, right? I mean, the idea is really basic. It's just that sort of mistakenly viewing a system as not conscious, that's to say a false negative in the context, would bring about more harm than benefits to the system. The idea is really simple, right? It's just, I think we probably all share the intuition. If we have consciousness and kind of are more inclined to protect that system that we consider conscious, right? So that's a really common view, and that kind of intuition also underlies the precaution principle that you find in work on animal sentience, where the idea is that it's better to be safe than sorry, right? So when we have mixed data on whether an animal is conscious, then we should treat the animal as conscious, just to be on the safe side. At least for policy making, right? I think other people suggest when it comes to science, there should be different views, but we'll come back to it later. And if you look at the literature on brain organoids and consciousness in these systems, you'll find also people writing things like brain organoids should be screened for advanced, potentially consciousness indicating cognitive capacities. And in general, these assessments should err on the side of overestimating rather than underestimating cognitive capacities. So the idea is that if we are not certain whether brain organoids have consciousness and treating these organoids as not having consciousness and cause harm to them, we should proceed as if they do have consciousness. Right, so this is, that's just a shared amount of information and taken most of us agree. So what I would like to do is now, I'd like to look at the science, right? I would like to look at the evidential standards of scientific studies of consciousness. So do the evidential standards, the benchmarks of accepting a claim in scientific studies of consciousness, do they align with this common normative intuition, right? That false negatives are particularly not. Or are, right, the studies normatively neutral? That's what we probably would expect, right? I mean, what are these evidential standards anyway? Maybe some of you are not familiar with sort of statistical significant. So let's just take a step back and take an example, right? Suppose you're an oncologist and you want to find out whether eating processed meat, cheeseburgers, whether that can cause cancer. So you may then take two groups of rats and feed one of these groups with cheeseburgers and the other group with veggie burgers, and then after 3 months or so, or after some period of time, you just take some sample from these from the rat's tissue, and you compare the rate of cancer cells, essentially. Suppose you find a difference, right? Then the question is this just a chance finding, right? Is it just a fluke? Or this kind of result? Is it a false positive? So what do? Well, scientists, they tend to, it's sort of standard procedure is to test the null hypothesis, right? Let's just say to test the view that there's really no difference between the two groups, right? And you sort of test the null hypothesis by calculating the p-value of your results. And the p-value is sort of value between 0 and 1. And it indicates a probability of your finding of the observed group difference, or a larger one, assuming that the null hypothesis is true. So if the null hypothesis is true, how likely is it to get this kind of result you've got? Right? And so the interesting, crucially too, the p-value is between 0 and 1, and scientists, before they run their study, they actually need to define what value they consider as sufficient, as enough to hold that the finding is statistically significant. Right? It's not a chance finding. And by defining that kind of threshold, they set the specific false positive and false negative probabilities that they are willing to accept. Now, when it comes to the false positive probabilities that they're willing to accept, that's sort of called the alpha level, or alpha. And across the sciences, it's currently still standard to set the alpha to 0.05 or less. And that then just means that there's only a 5% risk that the result you get is a false positive. But this threshold, and it's also really important here, is arbitrary. So you can also set a different alpha level, but typically it's kind of by convention, people set the alpha level to 0.05. Now, when you run a study, you don't only want to make sure that you don't commit false positive mistakes, right? You also want to make sure that your study is really sensitive enough to pick up the effects that are being out there, right? So you want to make sure that you also avoid false negatives. And the indicator of how small an effect your experiment can detect is called the power of the study. And it's specified as 1 minus beta, where beta is the false negative probability. Now, scientists, they commonly set beta, that's to say the false negative threshold, to 0.2, and that gives them essentially an 80% chance to detect an effect if there is one. But just like the alpha level, the beta level is also just arbitrary. It's kind of a conventional benchmark, and people use different beta levels. If they want to aim for higher power, they may set a lower beta. But study power is actually related to sample size, so that if you hold your alpha constant or fixed, then, and if you want to have higher power, then that requires larger samples. And that tends to be a bit of a problem to get larger samples. So typically it's people aim to get a power of 80% and to have a beta of 0.2. But we're going to come back to this later. It's relatively rarely achieved. So what I wanted to say here really so far is only the basic point that it's common in scientific studies in general to accept an alpha level of 0.05 and a beta level of 0.2. Now, can you remind me how much time I have?
So 30 minutes?
30 minutes left, okay. So the question now is, do studies of consciousness, do they also rely on these evidential benchmarks? And So you can run different studies, right? When you study consciousness, you can do qualitative studies, or you could do quantitative studies that don't involve any particular group comparison or any hypothesis significant testing. But both of these two benchmarks that I've just mentioned, they're actually also applied in the consciousness studies. So, for instance, Nick Shea and Tim Bain, who's I think also in the audience, and Jonathan Birch, in their papers on sort of consciousness detection problem, they've mentioned experiments on trace conditioning. Right? And in these studies, so participants, they could actually form a link, an association between a tone and a puff of air to the eye, so that this tone sort of triggered an eye blink when the puff of air to the eye occurred or was administered during the tone occurrence. That's called delay conditioning. But interestingly, for trace conditioning, and that is when the air puff occurs briefly after the tone has stopped, then people didn't really learn this connection. They didn't really acquire this eye blink response unless they were also conscious of the link, the contingency between the tone and the puff of air. And so consciousness seems to be involved in enabling this kind of learning, and that's why Nick and Tim Bain and John Birch, in fact, lots of people have said or suggested that trace conditioning may actually be a matter of consciousness. Right, but for me, really, the point is only that these studies they used null hypothesis testing, and they set the alpha levels to 0.05. And so most of these studies that philosophers have cited in their work on the detection problem, most of these studies, they rely on that alpha level. And this is totally unsurprising, because lots of studies on consciousness, studies that explore the link between psychological and behavioral capacities in consciousness. Lots of journals that publish these articles on an issue, they actually require this sort of significance level of the p-value below 0.05. So consciousness researchers, even if they wanted to, they can't really get around accepting that significance threshold, because it's sort of a requirement for publication. Okay, now I don't know why the alpha and the beta values look so strange in these slides. It didn't look like that when I actually made the slides. Sorry about this. Anyway, so that was just about the alpha levels. But lots of these studies of consciousness that we're talking about, they also set their beta levels to the conventional 0.2 or higher. That then corresponds to some lower power. Now, actually, in fact, lots of new scientific studies, including experiments on consciousness, so this is the goal, right? So they want to have a study with this kind of power. But typically, if you look at the meta-scientific studies, it actually measure how much power these studies tend to have. These studies found that typically neuroscientific studies on consciousness, for instance, we have much lower power. And if anything, their beta level is often higher than 0.2, because their samples are just notoriously too small. Why is that? Well, because researchers have limited resources. They don't have the money to sample lots of people. But interestingly, there's even a more important problem, right? When it comes to neuroscientific research, when you run invasive studies, that is actually ethically problematic, right? Because recruiting more participants, more chimpanzees or more rats, for invasive studies, in many cases, that means at some point killing your participants. And so in this case, recruiting more participants is just ethically really problematic, and I don't like that. So it would potentially mean more death, right? So it's not really an option. So it's difficult in the science of consciousness or scientific studies on the correlates of consciousness and consciousness effects to achieve a beta level of 0.2 through large samples. So again, the basic point here was really only that there's reason to believe, in fact, it's sort of kind of fact, that many studies of consciousness, they do have the standard alpha of 0.2, so 0.05 or lower, and the standard beta of 0.2 or higher. Now, I've talked a lot about sort of alpha and beta levels, and you might think, this is very should they care, right? So I think it actually is really important to think about these evidential benchmarks, right? And why does this matter? Well, we can now return to the initial question that we started out with, and that was, do studies on consciousness, do they generally capture the reasons for its negatives in consciousness ascriptions are worse than false positives, or are they just normatively neutral, as many of us would expect? Well, given what I've just said about these sort of evidential standards in science in general, and then also by extension in lots of studies on consciousness, we can actually answer that question with a no, right? Why? Well, because lots of studies, scientific studies on consciousness that search for neural correlates or consciousness effects in general, they will need to accept the standard or the conventional alpha level and beta level. And that just means that these researchers then accept only a 5% false positive rate, but they accept a 20% false negative rate. And that's just to say that false negatives in that kind of research are viewed as 4 times less problematic than false positives. Now, this is kind of exactly the opposite to what we started out with, right? Because we started out with the idea, the intuition, that false negatives may be particularly problematic or more problematic than false positives. And now it turns out that actually, when you look at the evidential standards underlying scientific studies, it's quite the other way around. Now, why is that so anyway, right? Why is it that the false positive threshold is lower than the false negative threshold? Well, there's lots of reasons, but one reason is publication bias, and that's just the idea that, or the problem that positive findings, statistically significant findings, are more likely to get published. Now, that's okay, but it means that then your corrections of the false positives, and these will be replication failures. And that means your finding is not sort of statistically significant. That means that those corrections, right, they are less likely to get published. And it has the negative upshot that then false positives, they can become kind of ingrained or kind of established within a field. Right? And that is really bad because you could have junior people that then just look at these positive findings and then they build their theory on it, they run further studies on it, and if it turns out that these positives were actually false positives, then lots of effort, money, and so on is wasted. Right? And so this isn't just fiction, this isn't just hypothetical, this is actually, there's lots of evidence that lots of studies do not really replicate, right? This is the crisis, the replication crisis. In the natural and social sciences. And so because of these replication failures, a lot of people have now been pushing for a further reduction, right? Or in fact, a reduction in the current conventional alpha level from 0.05 to 0.005, right? So can you tell me when I have to stop exactly?
Depends how many times you want for discussion, but normally in half an hour, normally in 10:30.
10:30?
Yeah. Yeah, 10:30 in 30 minutes, but if you...
Okay.
You started a little late.
Yeah.
Closer to 9:40.
So I'm not a great fan of lecturing, so I'd like to do this more interactively. So I'm just going to rush quickly through it so that we have a little time. Okay, so this is, I think, this is already clear, I think. And why, I mean, we could equalize for levels, right? So that we have essentially that the false positive and false negative is equally low. We could do that. Well, I mean, maybe we could, like theoretically. But if you look at it, if you think about it, then reducing beta to even only the 5% level to match the current conventional alpha would require increasing a study's power from 80% typically, 80% to 95%. And that just requires a much larger samples than people commonly have in studies in general, and especially in the neuroscience, especially in the kind of for us interesting studies, right? The power is really low. Typically, the power of these for us interesting studies is actually only 50% lower than that. So, and again, this isn't quite an option for consciousness researchers or experimental researchers to recruit more people, because again, they're like resources and they have ethical ethical limitations. And so the problem is actually made much worse if you now factor in the idea in the meta-science debate that we want to do something about replication failures. Because if you reduce the alpha level further from 0.05 to 0.005, then because there's an inverse relation between alpha and beta, that just means that if you reduce your alpha level further but keep the sample size the same, then automatically the beta levels is going to go up, right? And so if you keep pushing for further reduction of the alpha levels and also factor in that increasing the sample size isn't really an option, that just means that your difference is going to go up. And then again, so we could, given that there's this inverse relationship between these two evidential standards, we could also obviously lower the beta level without increasing sample size, but that just then would require us to water down the alpha level. But researchers can't really do that because they've got the provocation modes to deal with, right? They need to have an alpha level that's below, a p-value is below 0.05 to get stuff published. So there's this interconnected constraints. They kind of make it really difficult for, not all, but for many consciousness researchers that run experiments so they actually, these researchers, they need to, they are kind of forced to set alpha to 5% or lower and beta to 20% or higher. So within the classical statistics framework, scientists, as I just said, they seem forced to accept this kind of value judgment that false positives are more undesirable than false negatives. And as I said, this is kind of really the opposite of what we probably intuitively want. Now, so I think this is already really clear, but maybe just as an illustration, so there's this nice study by Appel. Is it Appel or Apple? How do you pronounce that?
I don't know.
So Appel and others. So they wanted to find out whether hermit crabs, whether they feel pain, right? And so the idea there was that hermit crabs, so do they display trade-off behavior? So do they trade off their response to pain against other motivational requirements, right? This is one kind of, this motivation trade-off is one criteria for being to kind of have pain experience. So what they did was they took these crabs and the hermit crabs, they were housed in either preferred or unpreferred shells, and then they gave them electric shocks of increasing intensity to their bellies. Right? And then they just looked at whether these crabs would abandon their cozy shells. And what they found was that actually, as predicted, if pain is involved, hermit crabs in preferred shells left the shells at significantly higher voltages than those in unpreferred shells. And so the p-value there was 0.036, and Appel and Elwood, they therefore conclude that pain is felt by hermit crabs. But suppose that their p-value had instead been something like 0.07. Then given that they set their alpha level to 0.05, then they would probably have concluded there's no evidence that hermit crabs feel pain. But that's problematic, right? Because they would then have taken a 4 times higher risk of missing evidence of pain than of mistakenly concluding that crabs feel pain when they can't. And it seems clear enough that the first kind of risk is more harmful to these animals, and that this first kind of risk is ethically problematic. Now, you may think that maybe this is just all no one is really going to base any judgments or decisions on whether there's an unconscious being or a conscious being or an unconscious process or unconscious process on these p-values, right? It just seems already idiosyncratic. But actually, if you look at studies on implicit processing, right, studies on subliminal priming, subliminal perception, then you'll find that researchers, they often prime participants with some stimulus, and then they run some behavioral measures to see whether stimulus will make any difference to their responses. Crucially, in these in that kind of paradigm, they also need to test whether people were actually aware of the stimulus. And what they do is they run awareness checks. And the idea there is just to, give these participants recognition tasks, right? Are they able to discriminate the stimulus? Did they ask them to see that, for instance? And the idea there is that if they perform a chance, and that's to say, if the p-value is above 0.05, if they display this kind of performance, then the researchers, they tend to infer that, okay, so the stimulus was processed unconsciously. Now, there's lots of problems here, right? Because you can't really, that inference is problematic, right? But that's what they do. That's what lots of them do, not all of them. It's not just me saying this. This is actually a systematic literature review. It's a bit dated, but Verdillo and colleagues. So that's what they do. And in this kind of, when they do this, they kind of routinely accept a 4 or more times higher risk of false descriptions of unconscious processing than a false description of conscious processing. Now, just to be clear, so I don't mean to say that this asymmetry is per se problematic, right? I mean, it's really only problematic when it comes to a particular null hypothesis, right? It's only problematic when the null hypothesis is that the participant is not conscious or not conscious of something. If the null hypothesis were that the participant is conscious, right? So if the presence of consciousness was the null hypothesis, then the risk balance connected to the standard alpha and beta levels would actually align with our intuition that false negatives are worse than false positives. Because these alpha and beta levels, they would then mean that mistakenly rejecting that the subject is conscious is considered 4 times or more worse than mistakenly accepting this news. But the problem is, these days, researchers that work on sort of that experimentally explore consciousness, they don't have this null hypothesis. They don't assume that, that the presence of consciousness is sort of what we can take as the given. Right? And that may probably because people are just reluctant to ascribe consciousness to animals. So they have the priors are just not sort of the right ones at the moment. And so, and maybe this is sort of my kind of almost last point. So there's also an epistemic problem, right? Because the set of truths that are discovered in a given scientific domain is smaller than it would be if false positive and false negatives had an equal chance of being followed up. And this problem is actually particularly kind of pressing or urgent when it comes to the kinds of studies that we're interested in here, like the detection of consciousness effects. Because this is a really tricky area of research. And what we want to do there, I think, and David Chalmers and others, too, is we want to let 1,000 flowers bloom. So we want to encourage discovery, right? But the problem is that the current alpha levels just is doing exactly the opposite. Because it privileges the avoidance of false positives over the avoidance of false negatives. And as I said, these recent efforts to tackle replication failures and sort of the idea to reduce the alpha level further is going to make matters worse because it's going to probably increase the risk of consciousness researchers overlooking consciousness effects. And sort of this is, I've got some suggestions here, but I think I'm just going to stop. So maybe we can talk about the suggestions then later. All I wanted to say is really only that there's this value judgment underlying scientific studies of consciousness, and I think this value judgment is kind of being overlooked at the moment. And it's actually a value judgment that is something that we probably would reject upon reflection. But there are people like Jonathan Birch, for instance, who write things like, when inferring the presence of credible indicators of sentience, there should not be any lowering of standards with regard to the methodology of experiments or with regard to the analysis of experimental data. Now, there are probably good reasons for this view, but I want to suggest that sort of an unreflected acceptance of the current evidential standards may actually be a bit of a problem, because it may actually make the discovery of consciousness effects or science of consciousness harder. And if we factor in that, we also want to ensure that science is more reliable, and if we reduce alpha levels further, then this kind of the risks related to the current evidential standards may actually be get even higher than they currently are. So maybe we just want to reflect on this kind of value judgment. It's kind of a philosophical question that's tied to what scientists are doing, and I'm curious to think about it. Thank you very much.